Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the cosmic distance debate, or more specifically, how we know the distances to the far galaxies. We've been looking at distances to stars using parallax, and now we're going to be looking at the distances to extraordinarily distant objects, to systems of stars like the Milky Way, but much, much, much further. And this debate was one of the most important things that happened in the early 20th century, and we're going to see some of its history, and we're going to see how it resolved. But the real important thing is, as we look at these stars, we have no idea what their distances are a priori. We just see them as points of light in the sky. And whether or not they were distant objects has been the subject of wonder for thousands of years. And only in the early part of the 20th century did we finally get a glimpse at how far they are. So the distance problem is incredible because getting distances will always be the biggest technical problem in astronomy, and frankly, the most important thing to relate astronomy to astrophysics. Because if you don't have distances, you can't know the luminosity, size, mass, or the distribution space of objects. And without this, you can't understand their lifespans, how they were born, how they live, how they die, what they do, how they evolve, or anything. So distance is the key thing in astronomy, and it's also one of the most difficult things. All right, let's see how difficult. Very early on in previous lectures, we talked about the astronomical unit, and the astronomical unit is incredibly important because it forms the baseline for trigonometric parallax. Copernicus used geometry of the orbits of the planets in order to determine the relative distances between the planets, and that was something that could be done. But it took until radar was invented to really get very solid planetary distances using the speed of light and being able to reflect radar off of objects, such as Venus when it's at quadrature from the sun, so it has a phase of a quarter phase as we see it, and that allows us to measure the distance to Venus relative to the sun and give us the astronomical unit by simple ninth grade geometry. And therefore, we can use trigonometric parallax, which is the measurement of distant stars. But trigonometric parallax, which is the apparent motion of a foreground star with respect to much more distant stars, as a result of the Earth's orbit around the Sun and the apparent change of that location, has a distance limit. On the ground, the best you're going to get is 1/100th of an arc second, and that's going to be using adaptive optics. But the Hipparchus satellite in 1998 was incredibly good because it got out to about 1,000 parsecs. And that is an important distance measurement because that got the accurate distances to about 100,000 or so stars, roughly in that ballpark. The Gaia satellite, though, greatly improved upon Hipparchus in 2016 with its first data release that got to 1% of 1% of an arc second, which goes out to about 10,000 parsecs and has at least 1 billion stars inside of that area. So the Gaia satellite has radically improved distances using parallax, which means distances are much better known to many more objects, which allows the physics to be better known. So we're going to define a new kind of distance that is secondary to parallax distance, because parallax is the only geometric way of knowing things. It's the only direct measurement of distance, and that's why Gaia was such an important mission. But the luminosity distance is just as important. How you do it is you measure the brightness of some object in some filter, say, and then you have some way of knowing or estimating, guessing, positing, or VGing out of the air the luminosity of the object, and then you solve for its luminosity distance by applying the inverse square law of the brightness. And that's what we see here. D sub L is the luminosity distance equals the known luminosity of an object divided by the brightness that you observe it to be times that 4 pi, and you take the square root. So you have to know the luminosity first. So it helps to actually get the luminosity from, say, a parallax of an object. But that tells you something you need to know, which is the nature of a standard candle. A standard candle is something where you already know the luminosity a priori. And if you do know the luminosity before you take its distance measurement or its brightness measurement, then you have what's called a standard candle. And you can calibrate standard candles in many ways, but I just alluded to it before. Take the luminosities of nearby objects where you can get the parallax, and then you find similar objects using some sort of distance-independent property that they share. Maybe the spectrum, maybe some variability, maybe something, who knows, maybe it's got a smiley face. And you assume that the distant objects have the same luminosity as the nearby objects for which you have the good distances. That's interesting because the step 2 to step 3 assumes that the laws of physics are the same everywhere. And that's what we're always going to assume, that the laws of physics that are nearby us that we would measure in the laboratory apply to distant stars. So we can use the ideas of physics in order to reach out into the cosmos, because we really can't in any other way. So once we get that calibration set of standard candles, then you can measure them for things that are too far for parallaxes. But the trick is this distance-independent property. And every distance-independent property relies on physics, and so we must assume that the laws of physics are the same there as they are here. And in this little diagram, it shows, well, if you have a candle that's of known brightness, you put it farther away, it looks dimmer. And likewise, another distance-independent property is the physical size of something. So the farther away it is, the smaller it appears. But there's very, very, very few standard yardsticks. But there are a few very critical standard candles. And so one of the more important ones is the spectroscopic parallax, because you can easily get the temperature of a star by either looking at its spectral type or its B minus V color or some other color variation. And if you have a well-calibrated HR diagram, then you simply have to say, oh, I know it's this kind of star because the luminosity class tells me it is a bright giant, so therefore it's an A81 type star, not an A8 main sequence star. It's an A8 bright giant, not a dwarf. Dwarf would be dim, giant would be bright. And so you can then say, I've got the spectral type and luminosity class, and that's for stars, which are incredibly bright objects that you can see from a distance. Likewise, if you calibrate the HR diagram, then you could say using a known HR diagram, such as the Hyades, the Hyades then becomes the basis for all your other HR diagrams. And so the only reason the Pleiades looks different, its main sequence looks dimmer than the Hyades, meaning a V magnitude that is larger, but the same colors for the same stars, is because the Pleiades is farther away, and so the distant, they just are simply fainter and therefore have larger V magnitudes for exactly the same kind of star. So you calibrate all of these things, get distances to Pleiades, get distances to Hyades, and many other things, and the Hyades itself forms the basis for all of this calibration. So it is the most critical of all of the nearby clusters. And we can therefore build the cosmic distance ladder out of extraordinarily nearby objects. So what we have is a power of 10 in distance. Each time we go up 10, the number across the bottom means something's about roughly 10 times more distant than the other in terms of parsecs. And parallaxes get us out to, say, now much further than we had thought. But originally, the parallaxes got us out with Hipparchus only about 100 parsecs or so. But that's how far we can see now with the parallaxes, up to 10,000 parsecs. And we can use proper motions of stars in order to get us there. But then we can use parallaxes to get us to distant clusters with main sequence fitting. And that's where, or spectroscopic parallax work. But the next one we're going to talk about, the RR Lyrae and Cepheid variables, are incredibly critical because the study of the LMC, or the Large Magellanic Cloud, and then getting the distance to M31 is the subject of our next conversation, which takes us out to a megaparsec, or 10 to the 6th parsecs. So there were no ways to get parallax or proper motion, or even a group of stars that we would call a cluster in M31. So exactly how far is the Andromeda Galaxy, M31? You have to use RR Lyraes and Cepheids to get you there. So let's see how that was done historically. And the details are coming in, because off to the left on this thing with this picture from CTIO, we see the large and small Magellanic Clouds in the center of the Milky Way to the right, but the LMC is on the bottom and the SMC is on the top. And those clouds are actually galaxies, and they're orbiting the Milky Way, and that's what we know now, but we didn't know their distances. And what were those objects? And that was the study of the subject that we're about to talk about.